when equipment grounding conductors, or EGs, from both the primary and secondary sides of a dry type, or SDS, transformer are connected to the same ground bus, it creates a closed loop for circulating currents. These currents are induced by magnetic fields in the transformer core and windings. As the current flows through the loop, it encounters impedances in the conductors, connections, and transformer windings. These impedances cause a voltage drop across the loop, which in turn generates a humming sound. Let's delve deeper into the reason for this problem. In a typical transformer installation, the primary side, EGC, is connected to the primary neutral, which is usually grounded. The secondary side, EGC, is connected to the secondary neutral, which is also grounded. This configuration prevents circulating currents because there is no closed loop for the current to flow. However, when the EGC from both sides are connected to the same ground bus, it creates a path for circulating currents to flow between the primary and secondary windings. The magnetic fields induced by these currents interact with the transformer's core and windings, causing the humming sound. Now let's talk about the solution. To eliminate the humming issue, only the secondary side, EGC, should be connected to the ground bus. The primary side, EGC, should be connected to the primary neutral, which is grounded separately. This configuration breaks the closed loop for circulating currents and prevents the humming sound. It is important to note that the primary neutral and secondary neutral should not be connected together because that would create a closed loop for short-circuit currents. To summarize, the humming in dry-type transformers when EGC from both primary and secondary sides are connected to the same ground bus stems from circulating currents induced by magnetic fields flowing through a closed loop with impedance. This impedance causes a voltage drop and generates the hum. The solution involves connecting only the secondary side, EGC, to the ground bus and connecting the primary side, EGC, to the primary neutral, grounded separately, thus breaking the circulating current loop. Always remember to keep the primary and secondary neutrals separate to avoid short-circuit current loops. Let's further explore the nuances of transformer grounding to gain a more comprehensive understanding. Grounding, in electrical systems, serves several critical functions, including providing a low impedance path for fault currents to return to the source, minimizing voltage potential between conductive parts and ground, and ensuring the reliable operation of overcurrent protection devices. In the context of transformers, proper grounding is essential for safety and performance. Incorrect grounding can lead to various problems, including the aforementioned humming, as well as increased risk of electrical shock, equipment damage, and even fire. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems, including transformers. It's crucial to adhere to these requirements to ensure a safe and compliant installation. The NEC specifies the types of grounding electrodes that are permitted, the methods for bonding conductive parts, and the sizing of grounding conductors. One common grounding electrode is a ground rod, typically made of copper or copper-clad steel. Ground rods are driven into the earth to provide a direct connection to ground. The NEC specifies the minimum length and diameter of ground rods, as well as the required spacing between multiple ground rods. Another type of grounding electrode is a concrete encased electrode, often referred to as a UFA ground. A UFA ground consists of a bare copper conductor encased in concrete, typically in the footing or foundation of a building. UFA grounds are often more effective than ground rods, especially in areas with poor soil conductivity. In addition to grounding electrodes, bonding is also an important aspect of transformer grounding. Bonding involves connecting conductive parts together to create an electrically continuous path. This helps to minimize voltage potential between different parts and provides a low impedance path for fault currents. The NEC requires bonding of various conductive parts, including transformer enclosures, metal raceways, and equipment grounding conductors. The sizing of grounding conductors is also critical for ensuring adequate protection. Grounding conductors must be sized according to the size of the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of grounding conductors based on the ampacity of the overcurrent protection device. In the specific case of dry-type transformers, the NEC has specific requirements for grounding. These requirements address the connection of the transformer neutral, the connection of equipment grounding conductors, and the bonding of the transformer enclosure. It's important to carefully review and understand these requirements to ensure a safe and compliant installation. Now let's discuss circulating currents in more detail. Circulating currents are unwanted currents that flow in unintended paths within an electrical system. In the case of transformers, circulating currents can be caused by several factors, including improper grounding, unbalanced loads, and harmonic distortion. As we discussed earlier, when EGC from both the primary and secondary sides of a dry-type transformer are connected to the same ground bus, it creates a closed loop for circulating currents. These currents are induced by magnetic fields in the transformer core and windings. The magnitude of circulating currents depends on several factors, including the voltage induced in a loop, the impedance of the loop, and the frequency of the current. Circulating currents can have several negative effects, including increased losses, overheating, and equipment damage. In addition to causing humming, circulating currents can also lead to premature failure of transformer windings and other components. To minimize circulating currents, it's important to follow proper grounding practices and ensure that loads are balanced. Harmonic distortion can also contribute to circulating currents. Harmonic distortion is the presence of harmonic frequencies in the electrical system. Harmonics are multiples of the fundamental frequency, such as 60 Hz in the United States. Harmonic currents can flow in the neutral conductor and in ground conductors, leading to increased losses and overheating. To mitigate harmonic distortion, harmonic filters can be used. Harmonic filters are designed to block or reduce the flow of harmonic currents. They are typically installed at the load or at the source of the harmonic distortion. Impedance plays a crucial role in the flow of circulating currents. Impedance is the opposition to the flow of alternating current. It consists of two components, resistance and reactance. Resistance is the opposition to the flow of current due to the material's properties. Reactance is the opposition to the flow of current due to inductance or capacitance. In the case of circulating currents in transformers, the impedance of the loop is determined by the resistance and reactance of the conductors, connections, and transformer windings. The higher the impedance, the lower the circulating current. Conversely, the lower the impedance, the higher the circulating current. That is why proper grounding techniques are essential to ensure that circulating current is minimized by breaking the loop. Understanding grounding electrode systems is also critical. A grounding electrode system is a means by which an electrical system is connected to the earth. The purpose of a grounding electrode system is to provide a low impedance path for fault currents to return to the source. The NEC specifies the types of grounding electrodes that are permitted, as well as the requirements for installation. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. Ground rods are typically made of copper or copper-clad steel. They are driven into the earth to provide a direct connection to ground. The NEC specifies the minimum length and diameter of ground rods, as well as the required spacing between multiple ground rods. Ground plates are typically made of copper or steel. They are buried in the earth to provide a larger surface area for contact with the soil. Concrete encased electrodes, also known as U for grounds, consist of a bare copper conductor encased in concrete. They are typically installed in the footing or foundation of a building. The NEC also allows the use of metal underground water pipes as grounding electrodes, but only under certain conditions. The water pipe must be in direct contact with the earth for at least 10 feet, and it must be electrically continuous. In addition to the grounding electrode, a grounding electrode conductor is required to connect the electrode to the electrical system. The grounding electrode conductor must be sized according to the requirements of the NEC. It must be made of copper or aluminum, and it must be protected from physical damage. The grounding electrode system must be properly installed and maintained to ensure its effectiveness. The connections must be tight and corrosion resistant, and the electrodes must be protected from damage. Regular inspection and testing of the grounding electrode system are recommended to ensure that it is functioning properly. When troubleshooting humming in a dry-type transformer, it is important to systematically investigate the possible causes. Firstly, visually inspect the transformer for any signs of damage or loose connections. Check the grounding connections to ensure that they are properly installed and tightened. Verify that the primary and secondary EGC are not both connected to the same ground bus. Use a multimeter to measure the voltage between the primary and secondary neutrals. If there is a significant voltage difference, it may indicate a grounding problem. Measure the current in the grounding conductors to check for circulating currents. A clamp meter can be used to measure the current without disconnecting the conductors. If circulating currents are present, try disconnecting the primary side EGC from the ground bus. If the humming stops, it confirms that the circulating currents were the cause of the problem. If the humming persists, investigate other possible causes such as unbalanced loads or harmonic distortion. Use a power quality analyzer to measure the harmonic content of the current and voltage. If harmonic distortion is present, install harmonic filters to mitigate the problem. If the loads are unbalanced, try to redistribute the loads to balance them. If none of these measures resolve the humming, consult with a qualified electrician or engineer. The problem may be more complex and require specialized expertise to diagnose and resolve. Remember, safety is paramount when working with electrical equipment. Always de-energize the transformer before performing any inspection or testing. Wear appropriate personal protective equipment, such as safety glasses and gloves. Follow all applicable safety procedures and regulations. In conclusion, understanding the principles of transformer grounding, circulating currents, and impedance is essential for troubleshooting and resolving humming issues in dry-type transformers. By following proper grounding practices, mitigating circulating currents, and addressing harmonic distortion, you can ensure the safe and reliable operation of your electrical system. Always consult with a qualified electrician or engineer if you have any doubts or concerns. Consider a scenario where a dry-type transformer is installed in a commercial building to step down the voltage from 480 volts to 208/120 volts for general lighting and receptacle circuits. After the installation, the building occupants complain about a noticeable humming sound coming from the transformer. The facility maintenance personnel investigate the issue and discover that the EGC from both the primary and secondary sides of the transformer are connected to the same ground bus in the transformer enclosure. Based on the knowledge gained from this discussion, they realize that this configuration is likely creating a closed loop for circulating currents, which is causing the humming sound. To resolve the issue, they disconnect the primary side EGC from the ground bus and connect it to the primary neutral, which is grounded separately. After making this change, the humming sound disappears, and the building occupants are no longer disturbed by the noise. This example illustrates the practical application of the principles discussed and highlights the importance of proper grounding practices in transformer installations. Another aspect to consider is the impact of different types of loads on transformer grounding. Linear loads, such as incandescent lighting and resistive heating, draw current in a sinusoidal waveform. Non-linear loads, such as electronic ballasts, variable frequency drives, and switching power supplies, draw current in a non-sinusoidal waveform. These nonlinear loads can generate harmonic currents, which can flow in the neutral conductor and in ground conductors, leading to increased losses, overheating, and equipment damage. When nonlinear loads are present, it is important to properly size the neutral conductor and the grounding conductors to accommodate the harmonic currents. The NEC provides guidance on sizing these conductors based on the expected harmonic content of the current. In some cases, it may be necessary to install a separate neutral conductor for nonlinear loads to prevent overloading the existing neutral conductor. Additionally, harmonic filters can be used to mitigate harmonic distortion caused by nonlinear loads. Harmonic filters are designed to block or reduce the flow of harmonic currents. They are typically installed at the load or at the source of the harmonic distortion. The selection and installation of harmonic filters should be performed by a qualified electrician or engineer. Proper grounding is also essential when dealing with sensitive electronic equipment. Sensitive electronic equipment, such as computers, servers, and medical devices can be susceptible to electrical noise and interference. Electrical noise can be generated by various sources, including lightning, switching transients, and electromagnetic interference from other equipment. Proper grounding can help to minimize electrical noise and interference by providing a low impedance path for noise currents to return to the source. Isolated ground receptacles are often used for sensitive electronic equipment. Isolated ground receptacles have a separate grounding conductor that is not connected to the building's main grounding system. This helps to prevent noise currents from flowing through the equipment grounding conductor and interfering with the operation of the equipment. The isolated ground conductor must be run directly back to the main grounding electrode system. It should not be connected to any other grounding conductors along the way. Surge protective devices, or SPDs, are also used to protect sensitive electronic equipment from voltage surges caused by lightning or switching transients. SPD diverts surge currents to ground, preventing them from damaging the equipment. SPD should be installed at the service entrance and at the equipment level. They should be properly grounded to ensure their effectiveness. Regular testing and maintenance of SPD are recommended to ensure that they're functioning properly. In summary, proper grounding is essential for the safe and reliable operation of electrical systems, especially those with transformers. It is important to follow the requirements of the NEC and to consult with a qualified electrician or engineer to ensure that the grounding system is properly designed and installed. By understanding the principles of transformer grounding, circulating currents, impedance, and harmonic distortion, you can effectively troubleshoot and resolve humming issues and ensure the protection of your electrical equipment.